And what I want to take a look at next is the function f of x is equal to sine of x. Now, so far we've talked about the function, or we've talked about the sine, and we've been calling it a function, but really we've been referencing it in terms of a triangle, a right triangle. But now we're going to talk about this function, f of x is equal to sine of x, in the same way that any other function you've talked about so far in your algebra background. What I have here is a representation of, this is, when we're at this side of the picture, this blue side of the picture here, what I have here is affixed to the wall, I have the coordinate system. Here's the x-axis, here's the y-axis, and I have the unit circle sort of fixed to this wall. And so this point corresponds to the point 1, comma 0. This is the unit circle, and it corresponds here to the point 0, comma 1, negative 1, 0, and 0, negative 1. So I have, think of this as being the unit circle. And now what I'm going to do with this is something that we haven't really discussed before. But there's a notion that we're going to call wrap, W-R-A-P, wrap the number line. And it corresponds to sort of a physical process. And once we have this notion of wrapping the number line, it's going to allow us to talk about this function in the same way that we've talked about other types of functions. Now, recall when you first talked about, let's say g of x is the square function, what does that represent? It means we choose a value of x. We are free to choose any value of x in the domain of the function. And we know for the square function, the domain is all the real numbers. So we choose a value, and then based upon that choice of the value, we do some sort of computation. Now in this case, in the most simple case, one of the most simple cases is we square the value. So if the value chosen is 4, the computation done is you square that number. If this value chosen is 4, this value becomes 16. If this value chosen is negative 5, this value becomes 25. And so it is some computation that we do, some algorithm, some process we go through to take the given input. Again, we think of this as being the domain, and we choose the x value, and from it will correspond to a range value, a y value here. And the way we compute this y depends upon the complexity of the function. But a function, all we're requiring is one input produces exactly one output. The specific computation we go through to compute the range value doesn't really matter, so long as we have a freely chosen independent value for the x coordinate, and then we compute the same y value. So given this, every time we're given the same input, we produce exactly that same one output. Now, the process of doing that computation is what we're going to be on about, and that is formed by this notion of wrapping the number line. So this is the idea. Imagine we're going to take this process of domain range, but we're going to use, rather than using some square function, we're going to use this process of wrapping the number line. And so the input, for our purposes, the input, the x value, the domain value may be any number of the number line. We are free to choose any value on the x-axis, any number line value. And what we will see is, over time, we will represent that as the domain is all the real numbers it's going to turn out. Well, we will see that. All right, so what do we mean by this? Imagine this string. I have a piece of string here, and I have a little blue dot taped to this string. Now let us imagine that I take this blue dot and put it at the origin of this coordinate system. All right? And imagine somewhere on, this piece of string now, this piece of string would now correspond to the x-axis. Every point that's on the x-axis corresponds to a point on the string. And so let's suppose I choose at random a value here on the axis. So there's my value on the x-axis right here. I'm going to mark that. I have a value on the x-axis. So this is my point. It's 1 point something on this horizontal x-axis. Now what I'm going to do is pick it up. So now I have picked up. This is the x-axis, all right? I can do anything I want with this x-axis. This is the same x-axis as here. What I'm going to do is this. You always do the same process. I'm going to take this point, which was the origin, and place it at 1, 0. That's always the start. Place the origin at 1, 0. And then, this is the rest of the number line. I'm going to wrap the number line around the unit circle. Now, since the number line is infinitely long, unlike my string, since the number line is infinitely long, we would continue to wrap the number line infinitely many times around the unit circle. Notice that's why positive values, because see my x-axis? Here's the origin, right? The positive x-axis values score up above. And so when I wrap counterclockwise, that's where the positive values fall. That's why positive angles are measured counterclockwise. See these negative values, see this part of the string, which is the negative part of the number line, they wrap this direction. Again, infinitely many times they wrap around this direction. That's why angles that are measured clockwise correspond to negative values. And so when we wrap this number line, remember my single point I randomly chose? Every point, no matter where we choose it on the x-axis, every point on the x-axis is now going to correspond to a point wherever it falls on the unit circle. So this point has fallen at that point on the unit circle. So every point on the x-axis will correspond to a point on the unit circle. And then I can take that point on the unit circle, that will correspond to a point, or excuse me, that will correspond to an angle in standard position. So that point, which came from a point on the x-axis, wrap around the number line, that or the unit circle, that corresponds to a point on the circumference, and that determines this angle. The measure of this angle in radians, is precisely the x-axis value that corresponds to this point. Because in this picture, this is R is 1, S is the arc length. Well, the length of that is precisely the x value that corresponded to that number on the x-axis. So S is precisely that number from the x-axis. R is the radius. And so S is equal to R times theta. Well, if R is 1, that means S is equal to theta. So this arc length and this angle are the same number. Now, there's something that we get from that. Every point, no matter where we start, every point on the unit circle will correspond to, every point on the x-axis will correspond to a point on this unit circle when we wrap the number line. Imagine if I take a point, here's 1, here's 2, here's 3, out here somewhere up beyond the scope of my picture out here. Out here is the number 3.141596. Out here is precisely the number pi. That piece of string would then be length pi. What is the circumference of this circle? This is the unit circle. We know the circumference of the circle is 2 times pi times r. But r is 1. So 2 times pi times 1, the circumference of this circle is precisely 2 pi, which means half the circumference is precisely pi. And so if I took the value way out here, and I don't know where it would be, if I took the value way out here on the axis of pi, so this is my value pi, right here where my thumb is, and now when I wrap the number line, that is going to be precisely the number that falls at the value of pi radians. So the number on the x-axis corresponds to the radian angle here. And so that's why pi corresponds to a straight angle, because this value of pi is precisely the value of pi on the x-axis where this came from in the first place. And so we are free to wrap the number line around this unit circle as many times as we like. Now, here's what that means in terms of our function. Suppose we're trying to find the sine, right? We're trying to find the sine. Now look, as we start at 0, remember sine is y over r, but r is equal to 1. So sine is the y value. So if I choose an angle here, if I just randomly select an angle here in the first quadrant, the sine of that angle is this y coordinate. Do we see this y coordinate? Right? And so look, as I choose the value, as I start from 0, and the angle increases up to pi over 2, look what happens to the y coordinate. It starts at 0, and the y coordinate gets larger and larger and larger and larger and larger until it maxes out at 1. The largest possible y-axis value is 1. And then as it sweeps through quadrant 2, the y-coordinate starts at 1 and gets smaller and smaller and smaller. And notice, the decrease here is precisely the mirror image of the increase over here. So as this increases in the first quadrant, as we increase in the first quadrant, so exactly mirror image do we decrease in the second quadrant. And then, as you sweep through the third quadrant, it continues to get smaller and smaller. This y-axis value, this y value rather, gets smaller and smaller and smaller. See, this y value is getting smaller and smaller until it maxes out in the negative direction at -1. But then as it sweeps through quadrant 4, this y value gets smaller and smaller and smaller. And so as the angle sweeps around, the y-axis value starts at 0, gets larger, and then it gets smaller back to 0. Then it gets more and more negative, and then it comes back to 0. Then it gets more and more positive up to 1, and more negative down to -1, and then come back up to 0. And no matter how many times we wrap around the unit circle, that pattern will continue, starting at 0, going up to 1, mirror image coming back down to 0, the exact mirror image, but now going down to -1, and now the exact mirror image coming back up to 0. And if we wrap the negative x-axis, we get the same effect, but now we start at 0, drop down to -1, then come back up to 0, then elevate up to +1, then drop back down to 0. And so the idea is this. This axis here is marked off as the same scale as this axis. So if this is 1, this is also 1 over here on this axis on the left-hand side. And so if I start at 0, that corresponds to a radian measure of 0. Radian measure of 0. What is the y-coordinate of an angle there? Well, the y-coordinate of that angle is 0. But as the x value increases, as we go through the first quadrant. Now, the problem here is this is marked off, as we typically do with algebra, we mark it off in units of 1, 2, 3. But this isn't convenient in units of 1, 2, and 3, because if I choose at random, if I choose the distance 1, see, this is the distance 1. But see, that's not going to correspond to anything special on this circle. That corresponds to this point. There's my angle of 1 radian. That's not a particularly useful value. What I want is the value pi over 2. Now I can approximate pi over 2 because I have my calculator. My calculator says pi divided by 2 is about 1.57 or about 1.6. So if I choose the value on this axis, which is about 1.6, this is pi, but it's not pi, it's pi over 2. This value is pi over 2. And so now what that corresponds to is this. If I choose this point, to be pi over 2 on my string. Now, when I wrap this around that circle, that unit circle, this point is going to fall precisely within the limits of my physical string. It's going to fall precisely at this top point, corresponding to pi over 2. Let's see if we can make that happen. So there's my pi over 2 value. I'm going to wrap my number line. And when I wrap it around here, this point falls exactly at that point on the unit circle. And so it is much more convenient to mark this off not in terms of 1, 2, 3, but mark this off. So when we talk about graphing the functions sine and the other functions, cosine, tangent, and so on, we don't mark off the x-axis in units of 1, 2, 3. We mark off the axis in units of pi over 2, pi, 3 pi over 2, and so on out the axis. At 0, what is this y-coordinate? The y-coordinate is 0. But as we sweep through the first quadrant, now as these angles sweep through the first quadrant, that corresponds to these points moving from 0 to pi over 2. I'm going to kill this because there's nothing special about 1 anymore. As we sweep through this first quadrant, this angle gets larger and larger. And so this y-coordinate gets larger and larger, maxing out at 1. At pi over 2, this y-coordinate is 1, corresponding to, at pi over 2, the y-coordinate is 1. So what happens is it increases, it gets larger and larger and larger, and maxes out at 1. But then as we sweep through the second quadrant, what happens to this value? It decreases back down. See, this y-coordinate decreases back down to 0. But it decreases in an exact mirror image to how it increased in quadrant 1. And so this decreases back down until you hit pi, it's exactly at 0. Now, if I were to extend this over, this black picture over further, I could extend down and continue this wave function. And so this is what it would look like if we had a larger picture. I'm going to move this down below my fixed unit circle here. So if this corresponds to pi, and this is pi over 2, and this is 1, and this is negative 1, then if this is pi over 2, this is 3 pi over 2, and then this corresponds to 2 pi, we have one complete revolution. It starts at 0, increases to 1, decreases to 0. See the y-coordinate, right? This y-coordinate increases to 1, decreases to 0. Decreases to negative 1, increases back to 0. So it starts at 0, it increases to 1. You could plot as many points as you wish, but this gets the basic idea. And then it decreases back to pi. And then it decreases down to negative 1, which is down here, and then increases back to 0. And so we generate this wave that's really badly drawn, this wave type curve. And then, is it clear what would happen as you go from 2 pi to 4 pi? That would be the second time around the circle. As we wrap the number line, we continue to wrap the number line, but all you do is repeat this cycle of going from 0 to 1, back to 0, down to negative 1, back up to 0, to positive 1 to 0, to negative 1 to 0. You continue that cycle, and so this would continue to oscillate all the way out as far as you would care to go. There is no limit to the number of times you can wrap the number line around the unit circle. Similarly, there is no end to this picture as it continues on towards positive infinity. And since we're also wrapping the negative part of the x-axis around the unit circle, this wave continues in this left-hand direction. And so that's the basic idea of the sine curve. Now what we'll do in the next video is I'm going to get rid of my old picture here and get a few more details of what this picture looks like. That's the structure of how we generate the sine curve. The cosine curve is done in the same way. Notice, by the way, what we're doing is we're taking, remember sine of t, sine of theta, it's y over r, but r is equal to 1. So sine of theta is the y coordinate. Remember cosine? Cosine of theta is the x coordinate. Sine is the y coordinate. We start at 0, and then it was, try that again. It was 0, it was 1, then it was 0, then it was -1, then 0, then 1, then 0, then -1. Cosine does the same effect, but now we're using the x coordinates. Cosine starts at 1 because we're using this x coordinate, this horizontal distance. And so cosine starts at 1, decreases to 0, then decreases to -1, then comes back up to 0, then comes back up to +1. So the cosine graph is constructed in a similar fashion. The details are slightly different, but the notion is the same. All of this comes from the notion of wrapping the number line around the unit circle. And so what we'll do next is we'll get some more detail on what the facts and the figures of the sine graph and the cosine graph.